Assalamu alaikum. Good afternoon, fellow ASME members and guests. We're delighted to have you all in our first series of our Ask the Expert. Today's session is with a special guest. He is a consultant in the field of rotating equipment and machinery reliability with over 30 years of experience. Please help me welcome Mr. Abdulrahman Al-Khowaiter. Welcome.
Thank you, Mohammed. Thank you very much.
Now, just to give you all a brief about this session, this is mostly a Q&A session where we want to ask our expert about his experience, his views on different mechanical engineering topics, and we get to hear back and ask. So feel free to share any of your questions or any of your comments in the comment section, and our moderators will direct these questions to me. Now, technical stuff. Let's ask you just a general question, Abdulrahman. What made you choose mechanical engineering as a major in college?
First of all, I'd like to say thank you, and thank you for all who registered with us today for attending. We'd like to share information among everybody. Everybody has gained experience over the years, and I'm happy to be a speaker, but also like to hear new ideas and experiences from others. In answer to your question, when I was 4 years old, I used to steal my father's toolkit and start playing with the tools. After 6 months of this, my father locked up the toolkit. And after that, I was trying to get into the toolkit as much as I could. And later, I was trying to play with all the toys possible and take them apart and build new toys ever since I was young. So I think by age 14, I realized the closest to my interest is mechanical engineering. And I joined college and graduated that way. After that, I worked for pretty much one oil company for 32 or 33 years, 32 years after graduation.
MashaAllah. So your passion started at a very young age, I see. So when you think about disciplines, now you're a machinery and reliability expert. What made you choose that when you had different options such as piping or static equipment, materials manufacturing? I mean, mechanical engineering is a very broad engineering discipline. So what made you choose that particular one?
I believe it's inbuilt in our internal interest. As we said, most of us actually sometimes discover the interest when we're young, from a young age. Others discover later on in life. Maybe sometimes people have reached and graduated, let's say, an engineering degree, then they realize it's not what they wanted. They got into law after engineering, and they became a lawyer, and by 24, that's what they want. So it depends on the person. So my interest was rotating or machinery, things that move, I would say, aircraft, trains, buses, engines, machines, anything that moves. Whereas others, you'll find they like civil engineering. There's things that don't move very much. And if they move, they've started failing. So they'd rather they don't move. So everybody has their own internal interests and skills.
So in terms of your job currently, you work as a consultant for machinery or reliability?
That's correct. Yeah, that's correct.
What do you find? Yeah.
Go ahead.
What do you find more interesting about your current job? What's the thing that keeps you motivated and driven every day when you go to work?
I would say the curiosity, number one, and learning something new is interesting. That's number one. Number two, and whether the learning is by reading or by seeing the problem occur in front of you, or somebody has related to a machinery problem, or failures, or performance problems, or either reading about it or seeing on the internet, attending conferences. It's all interesting. It satisfies our curiosity, human curiosity. The second interest I have is creativity. I like to see new ideas. I like to develop new ideas when I have the chance. You can't develop them every day along in your work spheres. A lot of times you're doing, everybody knows the day to day. But sometimes along the way you get problems, and that's a time where you can add your creativity and develop new solutions. This is just something I was working on about a month ago. I don't know if it's clear. Is it clear in the picture? Mohammed, is it clear?
Go ahead and try sharing your screen again.
It's not shared. It's in front of the camera. Do you see my camera?
Oh no,
I
your
don't know if it's
camera's
clear.
not open.
If I-
Tr-
oh,
Yeah, it's loud and clear.
the camera
Yes.
should be on. Yeah, you can see it in the camera
Yes.
because the camera says
Okay.
on. Yeah. Okay.
All right. Okay.
So it's a kind of plastic fiber reinforced polymer for laminate seals on gas compressors. And we developed it in-house using a special material, and it's running successfully now about 2 weeks with no problems, or 3 weeks, no, 1 month it's running. And it took a lot of creative work and modification. The original were aluminum seals. This is a high temperature material, suitable up to 330 Fahrenheit continuous, and it has better properties for sealing it's a centrifugal gas compressor API 617, and this is sealing the interstage laminates inside the machine, between the impellers and the shaft, things like this. And it is more efficient. It does not rub heavily, and will give a far longer life, and is corrosion resistant, completely corrosion resistant. So this is an example of a recent creative work. Thanks.
Okay.
The other issue you asked, what other things interest us along in the job, what keeps you motivated, is I would say solving problems and finding new problems to solving them. We work for plants to troubleshoot plants as consultants, and whenever they have problems, we try to find them. I branch out of exactly my own sphere of normal rotating equipment, get into instrumentation-related issues, process-related issues that affect our machinery. And I find it interesting to kind of come up with permanent root cause solutions. So that's another interest, which is root cause analysis of machinery failures or any failures in that we're faced with in our work environment.
It's very nice that you mention it, because one of the questions that we received is, how can you achieve zero maintenance when you don't have enough data on the topic? So when you have very limited data taken from the failure or from the assessment, how would you tackle that issue if you were to go about it from a reliability perspective?
Is the question about the zero failure in terms of once you've installed the machine, you're expecting zero failure, how to achieve zero failure from day one before the plant is designed, or they mean that the machine has been repaired and they want to see zero failure? It's not clear so much.
Assuming if you are three cases. Case one, you are the designer of this equipment. Case two, you are the end user of this equipment. And case three, you're a consultant or expert trying to solve this. How would you go about it when you don't have enough data on the information?
Okay.
It's a very broad question, I know, but it's something that I think most of our audience.
Yeah, zero failure is something as consumers we've come to expect. Not in all our consumer articles. Let's say cars, we have washing machines, we have ovens, we have dryers in the house, we have other equipment, machinery, dishwashing machines. We expect almost zero failure for much of its lifetime. This because nowadays, in the year 2020 years, we're seeing more and more reliable equipment. And that's occurred over the past, I say, 75 years or 80 years of manufacturers making appliances. And gradually things have improved, design and everything. So now a lot of them are actually practically zero maintenance. So you can say these are nowadays becoming zero failure. If you take a refrigerator, if it's a good quality brand, general good quality brands around the world, well made, you can expect, if it's located indoors, 15 years between actual failures, which is great. I mean, that's pretty much what we would call zero failure at that point. I don't think zero failure means 100 years. People would consider 10 years and above as being zero failures. Similar to our other appliances. If we come to industrial machinery, they haven't been forced into a situation, manufacturers, where they're asked to do zero failure. So consumers around the world and or users, industrial plant users, have not really brought up this topic with the manufacturers of how to achieve zero failure. It really starts with the designer and manufacturer, because the designer company is also the manufacturer. At this point, if you say, how do I achieve zero failure with industrial machinery, when they haven't been really pushed to design them that way, you have to become the designer enforcer. So we say develop high quality standards, purchasing standards that enforce reliability into the machine through everything, through metallurgy, materials, testing, performance, the design details, which are normally failing elements, bearings, seals, lubrication systems, auxiliaries, all of these have failure points in them. The important thing is to realize what these failure points are, root causes, and put them into your standard as items that must be prevented. But again, it is some creative work here to achieve that. Whereas manufacturers, it's not automatic. They're not benefiting from when the machine runs 10 years. You, the user, and myself, we benefit. 10, 15 years live with zero failures. They don't. They lose spare parts, and the extra invested money they put into this machine to achieve 10 years is not paid for them out front. You're giving them a bidding situation where it's a low bid, and in that low bid situation, the lowest bidder wins. So they say, why should I invest extra money and then lose the bid? Why don't I just do what makes it run 1 or 2 years, and then that's your trouble. So we have to think of these items, these critical issues, when we're purchasing machinery.
I see. Now, you talked about standards and about how you want to improve your purchasing requirements. Now, how do you see non-metallics as a way forward now, since the industry is moving towards things that are more lightweight, more sustainable, more sturdier in the industry?
Yeah, non-metallics is
it doesn't necessarily have to be
superior
in oil and
solution.
gas.
Yeah, well, I would say on all applications, that non-metallic are really a good solution for any item that's under corrosion, for example, as long as it's not a high temperature application. If it's a high temperature application, the non-metallics are a poor situation unless the non-metallic is ceramic. But I believe most of the talk on non-metallic is really discussing the polymeric type. Okay, now fiberglass, high density polyethylene, the many other normal polymers that we're used to. So these are limited to temperature ratings of, depends, if the HDPE, it is roughly 170 degrees Fahrenheit, 180 maximum. If it is fiberglass, they have some that go up to 250 rating, 250 degrees Fahrenheit rating. So therefore, these polymeric materials and non-metallics are greatly suitable for corrosive activities if they're below these temperatures. The other aspect is they're great for static equipment, like piping, obviously, great. If they're not under mechanical danger, meaning like firewater piping is typically above ground in our company, or depend on most companies, oil and gas. The firewater piping would be, in the old days, it was carbon steel. It would be rusting like anything on the inside. And they would have a cement lining, but it was a failing. The cement lining was a 100-year-old technology, 120 years old technology that was actually failing. And I was one of the ones in our company to push toward non-metallic like fiberglass or plastic. And obviously it works great underground. So the best solution for underground in this case, for water piping, is to have plastic HDPE or fiberglass. But when you get above ground, you need mechanical strength. It has to resist people bumping against it. It has to resist, could be a 4-inch pipe, could be a 6, could be an 8-inch pipe, whatever the diameter, could be bumped by a car lightly, and then if it's fiberglass, it'll break. Whereas the steel piping would just bend a little and that's it. It'll be perfectly fine. The other thing is above ground firewater piping has to be fire resistant, and the fiberglass is not, unless it's coated with very specific fire retardant materials, which makes it expensive. So carbon steel looks like suitable above ground, but below ground, it's a disaster. Perfect place for polymers. Again, we come into other areas. If I come to rotating equipment, it's used in chemical pumps, for example, the non-metallic. Although we have seen that they fail, the non-metallic are not very good on pump services because the fact that they're weak, much weaker than the carbon steels or the stainless steels. The factor of safety in terms of ability to resist piping strain and piping stresses is less than 1/10 of the original steel, more like 1 out of 20. So from a safety point of view, we shouldn't only look at reliability, we should look at safety, number one. Number two would be reliability. Safety point of view, they're not as safe as metal connections when they're proper metal, the metal here meaning corrosion resistant metal that would have been used on a pump flange or the pump body itself. So they are not as safe, even though they might seem that way, but they're not, because of the fact that they can crack and then the liquid will come out, and if it's a hydrocarbon or a poisonous liquid, it's extremely dangerous, it becomes. So the older solutions were used as a metallic casing with an internal liner of non-metallic polymer, like Teflon internal liner, and they function fine. The other application is to use maybe non-metallic. However, there's a few companies in the world who make pumps where they're machining it out of a solid plastic. Okay. Now that is the best solution, where it's a solid plastic that is fiber reinforced. So it's a fiber reinforced, high strength, high tensile strength plastic, but it's made in a rigid integral body and not cast. So it's a rigid integral one piece that's machined out of a solid. This gives it much higher strength, and they also use metallic inserts on the flanges. Thank you.
Okay, that's a very lengthy answer and very technical, and I hope our audience have understood clearly the differences between using it in static and rotating. Now, there's another question that we've received. The question is, what is your viewpoint on WEC, white etching cracks on bearing root causes, that has been written about lately?
Well, you know, I'm not an expert to the smallest detail on the chemical attack on bearings, but it's basically a chemical attack onto the bearing metals. And because I haven't really concentrated on this area, I'll just tell you from general experience on these, on when the bearing metal gets attacked by corrosive elements. Number one, it's the root cause is sensitive to the, first of all, bearing quality itself, the bearing metal quality like this. Now, bearings in the old days were more confining to one international standard of the vacuum melted steel, extremely high quality. You had the SKF and you have the VAG and the other internationally known, and there's only a few, and the Japanese ones. Then after a while, and then by the 1980s, more and more countries started coming into it, and you got lower qualities entering the market. So there's not one standard A. Now that we have an A, you got B, you got C bearings. So I would say stick to the A manufacturing countries, which have proven to manufacture top quality bearings, to ensure that your metallurgy is 100% correct. Okay, because the corrosion effect or fatigue on the balls and on the races or the raceways is a result of, number one, first of all, you start with metallurgy, how it was manufactured, the quality of it. Then number two, you come to the environment of how it was operated. So now we come to number two, environment. Obviously, everything depends on the quality of the oils, ability to separate the oil from any contaminants, which is dust and water and other corrosive elements in the air. Even, by the way, moisture in the air is a corrosive. So you don't need to have somebody pouring the water directly into the bearing and mixing with your oil. The problem is even moisture in the air. So we want to exclude moisture. Heinz Block pushed, Mr. Heinz Block, reliability expert, strongly pushed isolation seals to stop moisture entry and dust and dirt into bearing housings way back in the 1980s, after he retired in 1985 from Exxon. And at that time, people were just waking up to the fact that to go to exclusion seals on bearing housings. So the number one is to exclude these once you've purchased top quality bearings, and make sure they really are not fake bearings. Number two step is to isolate the bearing from all the bad influences, the environmental. Put in isolation seals, which are the double piece isolation type seals you have. They're made by Inpro seals. They're made by AES seals. They're made by SKF. SKF also has them. I can't recall exactly the name of the SKF, but it's a special name, something guard, I believe. And they have a rotating part on the shaft, and they have a stationary element, and they interlock, although they don't contact each other, interlocking. They're excellent exclusion seals. So you don't want to rely on the rubber seals, these lip seals and all this. This is 100-year-old technology, maybe 120-year-old technology, and it's really a wrong solution. And that's a failure right there. To install 120-year-old technology, which in the old days, they were happy if a machine runs 1 month without failure. Well, that's why they used to have these oil seals at that time. So don't use 120-year-old technology. Other chemical influences which could lead to these attack on the bearing is sometimes there's the obviously electrical fluting. It could cause a unusual coloring on the bearing. It would be caused by electrical arcing. So you have to check the amount of Gauss, magnetization of the shaft. Ensure the shafts don't have more than 5 Gauss roughly of magnetism in different axes, vertical, axial, and all different axes have to be checked with a Gauss meter. You have to make sure that the machine is properly grounded. If it's a motor, extremely well grounded in all aspects, and that would transfer electricity to your driven machines. So we say give the bearings a perfect atmosphere, perfect life, perfect oil, and they'll give you a very long life. Thank you. Hello?
Sorry, I had my mic muted.
Hey.
The question is, human curiosity is a good way to learn. He agrees, the audience member. Can you please advise on different ways where one can learn more about rotating equipment in general, or more specific disciplines in mechanical engineering from your perspective?
Well, the best is obviously to work with a company which operates a lot of rotating equipment. This is very important to start there, and the book learning is not enough. And you have to have working in such an environment, whether it's an electric power company who have such a lot of rotating equipment, or it's a petrochemical plant. You have the paper plants, maybe you have refineries, petrochemicals. Anywhere, any company which have a lot of machinery, you must start working in that environment. Then gradually build up maintenance experience, engineering experience in such an environment. At the same time, self-education now is so strong with the internet. We have the YouTube. I was looking about 10 years ago for videos on compressors, maybe a total of like 4 or 5 in the total on all the YouTube. Now there's maybe 500 just on compressors. It's the same with pumps. You find maybe 500 or 1,000. Excellent education. Some are lower quality, some are high quality, but there's definitely a lot of high quality education there. And the other is, of course, you should involve yourself in machine shops or repair shops. So if you don't get an opportunity to join a operating company which operates these rotating equipment, then the next best solution is to start with the repair shops. Large repair shops serve these refineries and petrochemical plants. They're independent. You can, if you get a job with them, you'll understand. You'll start to work with these machinery, understand a lot of details. And then later, again, try to go to them, either a designer, manufacturer of such equipment, or with the users, the petrochemical refineries, and all that. Otherwise, it's too difficult to get enough experience.
So is there a specific age that you would recommend someone to work at, let's say, a designer or a maintenance facility of sorts? Or would it be depending on the opportunity that someone gets? Like they always say that doctors take a few years to start off their careers, and then they become consultants, and then they become specialists, and so on and so forth. What would you say in terms of mechanical engineering, where one would, if one wants to go through the rotating equipment path or discipline, for instance?
Although, by the way, our call today is open to most all mechanical engineering issues, not only rotating equipment. But if I speak about the rotating equipment training, depends again on the job opportunities. Some people can get a direct job with a manufacturer like Sulzer or Flowserve or Dresser-Rand or Siemens, and they can get opportunities there to work on the field side, and they can get opportunity to work in the factory on the design side. So to mix the two would be great if you can mix the two. Otherwise, if you don't get that opportunity, yes, as we said, start with a user company which uses these equipment, machinery, and work on the maintenance or troubleshooting. Reliability units obviously is one of the best to be in. Start with a reliability unit if you can. Jumping to design and manufacturing is valuable. What I used to do is I used to read a lot of books on design and manufacturing to make up for this lack of direct design experience. And then later we went into reverse engineering of a lot of parts. So when you start going to reverse engineering, as you're there in maintenance or consulting, you will also definitely pick up a lot more in design, because when you reverse engineer, you have to understand the materials you're working with. You have to understand why they were designed a certain way, and then you can have the opportunity to create a better solution than the original manufacturer. Because if the parts were failing early, and it's not your fault, it wasn't a maintenance fault, then it's either manufacturing or design fault. There's your opportunity then to design it better, make it a better part, whether it's a steam turbine blade or it's a bearing, not a ball bearing, but a sleeve bearing of type, whether it's an impeller, because with impellers, you're not going to maybe cast it yourself, but you're going to help in the reverse engineering and then improve the engineering design of the impeller and give and have a local or international facility to cast the new improved impellers. So here, gradually, if you notice, you'll become a designer at the same time you're only working at a user company. Thank you.
All right. Now let's just shift gears to the future a little bit. Now, what do you think about 4IR and how we're integrating it with our industry? Where do you see the Internet of Things or big data or artificial intelligence linked towards mechanical engineering nowadays or in the future, possibly?
It looks like a 4IR is valuable for those companies who, number one, are not using a complicated distributed control system, which already has a lot of instrumentation on it. So they don't have enough instrumentation to begin with. So with 4IR, they decided, okay, we will add more instrumentation to get more artificial intelligence knowledge, and then to have a computer program that judges based upon that the additional instruments and the older instruments to make decisions for us or to assist us in making decisions. It starts warning you. This kind of solution is fine. For companies that are already well established and have strong distributed control system for their large equipment in their plants, they have a lot of instrumentation, they're going to see less benefits from a 4IR because you already have a 3.5 IR with the existing highly complicated equipment you already have installed, the highly complicated computers that are already there, and you have engineers who are specialists in the plant who are already using this information to troubleshoot the machines with their own minds. So it's not an artificial mind; it's an intelligent human mind. However, if your companies are going to have less of these well-experienced personnel, then they're going to need some artificial computer to take the place of the human to warn them. But then again, there's going to be errors in this artificial computer also, by the way, because the computer is going to always think that the sensors are correct. It's just like as a human makes mistakes, he thinks his mind reached a good conclusion, and he tells you, let's go to the right-hand side instead of left. He made a mistake. Actually, it wasn't. He should have gone left. But humans make mistakes, but machines also make mistakes. Or the AI will make mistakes, because in the end, AI is not the truth in the end, 100%. It's not always. Thank you.
Do you think one day that AI might be the 100% that we're looking for in the industry, so that we would rely completely on AI rather than having human interaction with equipment? Say
Yes,
in
if the robots are
machinery, for
developed
instance.
well enough, if the robots are developed well enough, there'll be a robot rotating equipment engineer, and he'll be going off to the machines and listening, and he'll do all the analysis with his own hands and sensors on his hands, by the way. And then his brain will, the internal electronic brain will find out the problem. Hopefully, it's been programmed, and it will go and talk to the foreman at the area operation foreman and say, "It's your fault, operation foreman."
Okay, shifting more towards energy. What do you think about the current state of renewable energies, whether it's in wind turbines, in geothermal, in solar? Where do you think it fits towards the growth of energy demand in the world?
You know, the number one reason is if people nowadays in year 2021 don't realize, okay, why wasn't the alternative energies utilized in a large scale before 40 years ago? Okay, 40 years ago would be roughly 1980, right? 1981. So the problem was that the price per megawatt or per kilowatt of those alternative electronics was too expensive. It was way too expensive compared to today. Therefore, the technology in general was there, but not the lower cost technology. For example, solar cells. You know, when I was young in high school, 1981, the solar cell price at that time, even for a larger scale, might be something like 10 times the cost of what it is today, maybe 8 times in our dollar cost today, something like that. As a total system, 8 times. So look at the price drop. I mean, that made it much more competitive with the hydrocarbon power generation, diesel power generation, or steam power from coal mining, or using coal-fired boilers, or from gas turbine-driven generators. All of these present power generation are now forced to compete against a lower cost alternative energy source like wind and solar for example, or tidal power could be also another one, that is able to produce power in the long term, because it's going to have failures too. The wind turbines, they have failures, they have maintenance costs. They are the same thing for the solar cells. Sometimes they have maintenance and certain failures in electrical components, whatever. So they also have a life cycle cost. But when you look at the total, let's say 20 or 25-year life cycle cost, they're coming out cheaper now, the alternatives, but only in the last few years, of course, they come out cheaper. So that means there must be the future, because they're coming out at lower cost on a 25-year or 20-year life cycle stage. And the hydrocarbons are going to go up, and they're limited by the finite life of the hydrocarbon which is pulled out of the ground. It's not none of it pulled out of the air. It has to come from the ground. The ground source resources are limited, which is crude oil and gases, and those will be gradually finishing in the next 25, 30, 35, 40 years. And we're going to end up with no hydrocarbons, gases and oils and others. We have to find a solution to that. Now, recently in Europe, there was Scotland in the UK. They're producing a lot of the offshore wind power of the United Kingdom. And they have a huge now 10 megawatt size installed windmills, wind turbines. And even they, of course, they have the older 5 megawatts. They have the 2.5 megawatts also. They're coming in with large power generation plants offshore. They are now developing a detailed design now stage for a hydrogen pipeline that will be coming from the offshore transmission location all the way. It's a hydrogen pipeline. It's a pipe with gas compressors that pump the hydrogen all the way back to London and to other main cities, Manchester and others, with this hydrogen line. And then the hydrogen, when it reaches the cities, will be used to directly produce electric power, either in gas engines or gas turbines, for example, or it can be sold as a hydrogen to fuel vehicles. So normal automotive vehicles can utilize the hydrogen. Of course, they have to be specially made for the hydrogen, obviously. But what I mean is now you have a direct from wind power. They're going to use electrolysis to produce hydrogen from the seawater, and then it's compressed and pumped into a pipeline, which reaches the mainland, reaches the main cities, and now that hydrogen is sold as a clean fuel. I don't know exactly the costs, but as you can see, it's not going to be too expensive, because the fact that you're producing from the wind, and this is a great opportunity to have a perfect clean resource. Now, don't forget something critical here is the oils that are being pulled from the ground, and they also carry with them NGLs, natural gas liquids, and they have natural gas. All of these carry critical materials, which are the basic founding chemicals of our plastics that we use. All the non-metallic plastics that we're utilizing have a hydrocarbon base behind them, practically all of them. I would say 99%, let's say, for example. So the oils are actually more valuable to us as humankind to be used as a final finished product than to be used as energy. So even though if we take over 100% electric power, that is basically 55% of the consumption of the hydrocarbons around the world, but 45% is going into, or 40, some people say 40, some people say 45, going into now production of plastics and other chemicals, and also certain chemicals. And we strongly need those chemicals for our modern industrial age. And they won't go away. That need will not go away. They have a major function.
So speaking about hydrogen, one of the questions that we've got is that it says, since the global energy industry is shifting towards hydrogen as a fuel, did you come across any studies to switch shipping pumps, compressors from gas to hydrogen? And what do you think the main challenges would be faced in that conversion?
I recently received a question on that to provide a technical analysis of it. And we replied that if it's engines, nowadays, I think it was Siemens recently started their hydrogen-powered, 100% hydrogen-powered gas turbine. And it obviously needs redesign of it needed design of the combustors and the blading, whatever. Mostly is a combustion chamber, because you want to have the proper mixture of the hydrogen with the air, and it burns at a high temperature, so you have to have the proper control of this temperature, so he doesn't overheat the gas turbine. However, practically all the gas turbines in the world, wherever they are, they can be fueled with a mixture, though. Instead of the, let's say, 100% natural gas, you could mix in, let's say, 25% hydrogen, and then you have 75% natural gas, and that doesn't take hardly any modifications. It's a minimum of controls and adjustment up to maybe 25% hydrogen. So a lot of the ones that are now using hydrocarbons to power them, you can have a mixture of hydrogen with them. The same for boilers, even boilers that are in steam power plants, whatever, that produce power generation, same thing. If you have dual fuel engine, you have gas engines, same story. A lot of gas engines are running on natural gas, for example. They might be power generation gas engines, or they can run on partial hydrogen fueled. Right now, it doesn't take much, slight modifications, slight controls. But there's a certain percentage that are not to exceed, because sometimes it can produce higher temperatures inside the combustion chamber, whatever. But in other words, it meshes in quite easily with our existing technologies.
All right. One other question we got says, do you encourage AI with experienced maintenance in prediction of problems in machinery in particular? And if I may add, in general, do you encourage AI to be used in maintenance in general, whether it's in machinery or in different types of equipment relating to mechanical engineering?
I believe it depends on the quality of the AI. I think, there was SAP, and you have certain other companies. They were producing better maintenance software. These maintenance management softwares are actually, they have an artificial intelligence in them, because they have what's called the plant maintenance package, which has advanced analysis. This is from, let's say, 15 years ago and 20 years ago, maybe mostly 15 and 10 years ago. Let's say they reached a point where they're quite good 10 years ago. These software are in your SAP or whatever your corporate software management system, which part of it is going to be for maintenance, part is for whatever other applications. Under that maintenance, you buy specific software, which is the maintenance management software. It can take in direct figures from your computers, from your online plant computers, whether it's a power generation or petrochemical or refinery or whatever it is. You have such computers. They will send the actual operating information to this software, and it could already trend problems and capture problems and give warnings, because it could be interconnected. They could be interconnected with the operational plant data, and come up with guidelines or warnings and like that. That is actually an artificial intelligence that was already there. But I think today what people are calling AI now is just a more thinking kind of software that takes in more of the data, then goes through many programming codes, which start to question the interaction of all the different information sources coming. For example, you have a high bearing temperature, you have a high vibration, you have this. So it wants to make a decision. Should it send a trip signal to the machine or wait and think more about it? It starts to analyze, almost like the human brain. Okay, wait, in the old days, we were doing that. We'd say don't stop the machine, let's check it first. Huh? But now with the AI, you can program it that way. It's already become the thinking part. It will check before it shuts down a critical machine, and analyze. Oh no, it'll make a judgment. Oh, this is a real problem, or it's a severe problem. Let's shut it down automatically. Something like that. If you look at, actually, they have similar AI also on aircraft, advanced aircraft. But sometimes the AI is not functioning so well, as everybody knows in the recent aircraft crashes. So I think we have to take AI with some salt added, because AI is just another failable element. Humans don't create anything that's perfect. So since we as humans are not perfect, the machines or the AI is not going to be perfect also. But can it help us? Yes. But I think we have to be careful. We have to still be in control of it. Thanks.
Okay. I mean, that's a very good perspective, considering that AI now can be developed to beat chess grandmasters in chess. So thinking about using it in reliability and maintenance, that would be a very big help for end users in general, or plant users. Moving on to 3D printing. Now, we have two questions on 3D printing. Now, the first one is, what's your perspective on printing rotating parts? So using metallic powder to print parts. Is there any limitations on the performance? Is there a trade-off of sorts?
Is this one here, is this clear here on the screen?
Yes.
Okay. So this is a example of a printed metal impeller, centrifugal pump impeller, and it was a sample where we had gone to a company that makes these. Basically start with a 3D CAD program, and they will take it and print any metal object you want. This is a stainless steel impeller printed, and you can see this is as printed condition. The quality is very high. It hasn't been polished after the actual printing. So you can get pretty much near net shape manufacturing from the metal additive molding or metal additive manufacturing process. Of course, if you had a shaft like this, see where the center of the shaft comes in, here you would do a final machining step. It would need a final machining step over here in the center of that. But that's pretty much about it. It's finished. It's ready to go after the machining that. The keyway and the shaft in the center. So if the question was, what is the applicability of plastic? Can you repeat the question exactly?
The question is, all right, just pull it up. It says, is there any impact in terms of performance limitations? And can you advise the general benefits or trade-offs when using 3D printed parts?
Well, okay. 3D printed parts, if they're plastic, they're easy to print. You can do them desktop, or your company might have a large plastic 3D printing. Then that's pretty much easy, except you have to be selective in the actual plastic printing, the plastic material itself that you're printing with, and they could get very good quality, shape, and everything. But the issue is it giving you the thermal properties? Is it giving you all the proper properties? You have to check. Nowadays, you have some that give peak and other plastic elements that are high temperature, whatever, and high what we call engineering plastics. So they will mold, or they will machine or mold not really machine. It's a final molded, you could say, 3D printed or 3D molded into a final shape that also has the engineering elements that we need: strength and resistance and heat resistance and all these features. And if that's the case, fine, they work fine in plastic. When you come to metal, it's difficult to get a metal molding, a metal 3D metal printing machine. They're very expensive, in the millions of dollars typically nowadays, and they need specialist operators. You can't just go and operate it yourself. They need specialist operators. They can do it on a continuous large scale manufacturing. It works fine. They can keep manufacturing different types to recover the money of the expensive cost of the machine. But you said, what are the limitations? Limitations so far are now on size. So they can't manufacture components. Many of them are limited to like 20 inches now. 20 inches has been about the limit. Most of these companies for the impellers, similar things. Maybe in the future they'll go up larger, back to 30, 36, who knows. But at this point, it's more like 18, 20 inches. And sometimes the costs can be high. So sometimes there's no big benefit from 3D printing it. Metal, I'm talking metal printing. It might be cheaper just to cast them with a normal casting company. For example, you have an impeller, you need a spare part. You might be doing reverse engineering. You got a 3D CAD drawing out of it. You send it to the casting company. They print it out. They can print a mold, okay, from whatever, a sand mold, foam sand mold, using their 3D printers, and then they cast into it directly using the old casting process, the stainless steel. Now you end up with carbon steel or stainless steel impeller, and it's not you're not using 3D printed metal in that case. But where can you use 3D printed metal? It's really nice for highly complicated geometries. Very highly complicated geometries makes the total cost much cheaper instead of all kinds of manufacturing machining steps. So in that case, they're a winner immediately. And in highly complicated metal geometries, without a doubt, they're a winner. But not when it comes to high stress fatigue parts. No, you don't want to do 3D printing of steam turbine rotating blades, for example. They don't have the properties of forged blades at all. But for steam turbine stationary blades, I think it's a great application to do 3D printing for them, because that's about the properties that are enough from a 3D metal printed. Of course, we're not talking plastics, talking metal printed. But rotating highly stressed parts, at this point, no. It's not the place for 3D printed metals. Maybe 50 years later, who knows? But for now, no. Thank you.
All right, thank you. We have another question that's about data statistics. Now, using data data statistics like Weibo analysis? How is it for optimizing maintenance strategies relating to rotating equipment? I'm not sure if this is the correct question, but this is what we have from our audience member.
Yes.
Was that clear or?
Yeah, it's clear. I see it being used. Of course, it's being used before my time. Weibull came from the 1950s. It was a Swedish mathematician, and he developed it. It's just really a statistical analysis of failures or of components with regard to their lifetime and their failure, number of hours in use. And it was originally made for manufacturing details, manufacturing defects, capturing with ball bearing manufacturers. They were having, obviously, this is the 1950s, for example. They need extreme precision and they need extreme accuracy and extreme reliability in the ball bearing manufacturing, because they're expecting a promised number of hours, operating hours life, an L10 life to their customers. They said, okay, we have a design bearing rating. There's a rolling element bearing. I don't have one now in front of me. We have a rolling element bearing. It's supposed to give in the 1950s. We sell it to a customer. We promise him 25,000 hours under this load rating. But the customer came back to us and says it only lasted 5,000 hours. It's a disaster for the company. Saying, hey, what happened? Is it your fault? Is it my fault? And then they found, of course, sometimes it was their fault. So there's a bearing, there's a manufacturing error in the total bearing, and they want to find out where is it, and which part is it? Is it the balls? Is it the race? Is it the assembly? Is it the final packaging as it went? Okay, so they need analysis. At that time, who has computers apart from the U.S. government and banks and the people have enough money to buy computers? Very few companies in the 1950s have any computers. You have to be very rich. Airlines were one of the first customers for large mainframe computers, by the way, because look at all the tickets you have and the huge amount of passengers coming and going. But they were able to spend that money. But the average companies, even maybe bearing companies, they didn't have any computers. So who's the best computer at that time? Humans. So humans at that time, they don't even have calculators. In the 1950s, they don't have calculators. None. There's no electronic calculators. There's mechanical calculators, but not electronic. Those came in the late 60s and then from the 1970s onward. So as a mathematician, he wanted to come up with a way to calculate and represent all these failures. So he came up with the Weibull process showing the failure rates and all this as a way to simplify the mathematics. That's all. There's nothing else. There's no magic in it. So I tell people that Weibull is just a mathematical calculation technique. It's not a reliability tool, even though it's used nowadays or it is spoken of as a reliability tool. I would say no, a screwdriver is a reliability tool. Weibull is not. I'm sorry, it is not. Weibull is a calculation tool. You can use it as a calculator, fine. But nowadays you have a desktop computer. Why would you need to use Weibull? Desktop with Excel can calculate much more. So Weibull analysis doesn't lead you to a more reliable plant, but statistical analysis of your failures will. Statistical analysis is just mathematics, simple. I have 100 failures of 100 pumps. Oh, okay, I put them into a table or an Excel sheet. Mechanical seals failed at this many times. You calculate it, all comes out. Okay, I have 5 mechanical seals that failed in the first 2 months. I have this. You can graph it also. So you don't have to use anything called Weibull. You could just do whatever, simple math or simple Excel sheets, which provide you all the data you want. But that's only the data. Okay, now you know the mechanical seals fail every 5 months. What are the failure modes? Does Weibull go and walk into the machine and check how the faces failed or why they're broken or why they overheated? No, it doesn't understand. It's just a simple mathematics. So it's been overinflated as a tool. And as far as I'm concerned, it's not even a tool. Your calculator is if it's a tool, then your calculator, the little, $5 calculator is also then a reliability tool, if that's a reliability tool. It's nothing more than that. Real reliability analysis, real reliability improvement comes from the human brain, at least now, unless 50 years later, AI will do it, using the human brain to what? Number one, purchase high reliability equipment before you even install them on the ground. 2, specify them. It's not just purchasing, it's specifying certain detailed design, detailed components, detailed procedures of installation that provide a high reliability during operation or after the next 25 years or 30 years of their life. This is real reliability. And then after that, when they do fail, how to do a root cause analysis. Can you send a Weibull robot that walks up to the machine and analyzes? No. So please, gentlemen, separate the real world from the false world. The Weibull is not a reliability tool at all. It's a statistical tool used for light bulbs. It's great for capturing light bulb manufacturer. It's great for ball bearing manufacturers, but it's not a plant reliability tool. Plant reliability needs a much wider, much more 3 or 4 or 5 dimensional thinking, 5-dimensional analysis. So I hope that's the answer to your question.
All right. Now on to more future and let's say forward thinking. Where do you see mechanical engineering in the next 5 to 10 years as a discipline? Now, if someone recently went to college thinking about, okay, I'm going to pick my major right now, where do you see mechanical engineering within the next few years? From you,
Yeah,
what's your own personal belief on it?
In a modern world, mechanical engineers will always find jobs in the widest areas of the industry. There's nobody who exceeds the ability of mechanical engineering degree to have extremely wide applications in the total manufacturing or industrialized world. Let's say, for example, we're talking India or United States or Europe or Japan or wherever the country is. Everybody now is shifting toward more and more industrialization overall. And I don't mean long smokestacks and power plants. I'm talking all kinds of industrialization, just building a parking lot and a highway and a roads. All this is industrialization. The highway needed industrial equipment, needed machines to manufacture that highway. It needed machines to carry the raw materials to bring them there. Needed machines to process the raw materials, the cement or the asphalt. The asphalt came from refineries. That all came from industries. All those industries needed machinery or needed mechanical engineers. Again, they put light poles along the highway. Same thing. Light poles came from factories. Those factories used raw material that came from other factories. Those other factories also needed engineers. Okay, they need electrical, they need mechanical, and some need civil. But mechanical was number one needed in all of them. So as long as we're going to be living in the future in the industrialized world, there's going to be a very strong demand for mechanical engineers. But again, it's quality first, gentlemen. The more you come from a high quality university, the more you will be in demand. The more you want to either save money or you have less opportunity maybe, or you want to have a faster degree. It's easier to graduate from a weak college, by the way. You don't have to fight for 5 years to get a degree and fight 5,000 smart students. If you're going to go the easy way, you're not going to be as valuable in the industry. So I would say for all young people who still have not graduated or before they even go to college, the best is to go the best possible school, quality, highest rated school that you can to get your skills up to a high level. And of course, you have the reputation of the school behind you that you graduated from. So there's a little benefit there. You have your own technical in your mind that you created, and then you'll have a more demand among jobs. And you also have the reputation of the universities that you graduated from. Thank you.
All right. Now, if you can give an advice, it was right to the point. If you can give an advice to your past self, like if you can go back, whether it's related to your career goals, your aspirations, what would it be? What would something that you would definitely want to tell yourself in the past?
Well, I think when I was younger, I wanted to be I studied mechanical engineering with a minor in aeronautical engineering. So I had always liked aircraft related. And then it was, as I graduated, I wasn't sure 100% whether I wanted to stay under a machinery track and go become a mechanical engineer in machinery, or whether I should go into aviation, because that was also a second love. But in the end, I felt more practical for myself. I decided the best thing is to keep that as a hobby and an interest and after hours, and then just stay on to my normal daily work, which is machinery and normal engineering, mechanical engineering. And that came out to be a good mix. So I get the same question, by the way, from the younger people. And they say, I have this interest and I like it a lot. But I have this degree, or should I go to here? I say, look, not everything has to be in your 7 to 4 or 9 to 5 operating working day. If you have a strong interest, you're an engineer, you have free time after that. You can use your engineering skills in your thinking and your development, or you want to make something in your garage, do it after hours. You got 8 hours after leaving work that you can use a free time and reading and developing whatever. Or it could be you go off to a night school and study at a university some in the courses that interesting things that you like to do. So the jobs don't really limit you because they're only 40 hours of your week. But how many hours do we have in the week? We have a lot more than 40 hours in a week. So I would say Yes, choose something, make sure that the job career that you choose is something you enjoy doing, but it doesn't have to be the perfect job for you. The other perfect side, that missing 25%, you can do it after hours. As long as you're happy 75%, that's good enough at that point in time. This is my view because not everybody's going to find exactly what they want every time. I got a question here. I just saw it from Mr. Osman. He says he works as a machinery maintenance engineer and he looks after a fleet of reciprocating machines in a gas compression facility. Okay, so reciprocating gas compressors. And he has a feeling that this field is really outdated in 2021. It's going to become more relevant in the future. As in a machinery expert, can you comment on this, please? Well, we did comment today on the hydrogen pipeline coming from the North Sea,
Scotland.
North Sea,
Yeah.
whatever, Scotland. Yeah, and I'm not sure if it's the Atlantic Ocean or in there in the North Sea. But anyway, main thing is that fleet is generating gas, and they're going to be manufacturing, making the pipeline in 1 or 2 years to carry that hydrogen, and it's going to need gas compressors to send it inland. So, but you're right. Your hydrocarbon gases probably in about 25 years might be finished at that time. But that means you got until the end of your career. They'll be working until another 25 years at least.
We have another question that asks, is FMEA a valuable tool in the industry, or is using experience to solve the mechanical problems a better option?
You know, FMEA was initiated by the Apollo mission as a strong basis for their analysis for reliability of the Apollo mission components, all the different elements, the Saturn V, the crewed vehicle that was going to go to the moon, and the crewed vehicles that were first being practiced to go around the Earth. All these use the FMEA because they didn't have time to operate it continuously, right? It's extremely expensive to operate them. But they would test them, of course, alone, each component as much as they could, but they couldn't test it all together. So they had to do the testing more as a theoretical testing. So you can look at FMEA as a theoretical testing of whatever the equipment is, machinery or electronics altogether. And whereas you also have physical testing. So FMEA is used more in the initial design stages, obviously. And you're trying to uncover problems with the design, and you come up with the failure modes, the FM failure modes, and you're trying to evaluate their effect on the operation or the integrity of the machine or whatever the device is. Is it a valuable tool? Yes, it's good to learn. It should be part of your courses that you take FMEA. It doesn't hurt to buy a book or read some good articles on it. It's good education. It's good for improving your standards. I was using FMEA on a more intellectual basis, not so much a written and into a tabular form. More, I would gather all the concepts and the failure modes I've seen and put them down in a notebook, one after the other, and then start tying them to, okay, root cause and finding a final solution. That's an FMEA also. Where you're doing failure mode analysis, failure mode and effects analysis. So the E is effects analysis. And then I'd improve the standards based upon it. But it's not a formal FMEA. It was an informal FMEA, not following the normal methods. And we came up with excellent standards resulting from this focus on, let's look at all the failure modes, why our machines are failing. For example, it was gas compressors, centrifugal, or it was reciprocating gas compressors, or centrifugal pumps, whatever they are. You come in and you have the years of experience that you have, you write it down in a notebook, all the failure modes. Then number two, you write other people's experience all down in a notebook. And now you have all these different failure modes under different processes and operating conditions. Then you start to say, okay, how could I prevent them? So it could either be a single person working alone, it works fine. But then also you can do it on a meeting level or on a brainstorming level, where you come up and you have a board and everybody writes down the different ideas, comes up with solutions. That's fine also. So FMEA can be multiple people, but can be you sitting down alone and doing your own FMEA. Is it valuable to normal operating plants? Yes, I would say that root cause analysis, when you have a failure, for example, on a machine, you should be using FMEA during the root cause analysis. Because yes, it's a machine that's already been built and operating, but now to find out why it failed, you need to do a failure mode effect analysis at that point to a certain degree. Okay. Somebody asked a question. He says he believes his question has not been answered yet. He said, would plant and end users consider energy efficiency as a factor in retrofitting machines in terms of compressor seals, gearboxes, rather than capital costs based upon your experience? Would plant end users consider energy efficiency as a factor in retrofitting machines? Yes, of course. Obviously, definitely, sure. I mean, when you're going to retrofit machines, usually it's a combination of issues. You want to improve reliability of the machine, and you'd like to improve efficiency. Okay, so that in that case you would retrofit, because your question was on retrofitting. However, other time, and you said what's the impact on the capital costs? You have to put all the costs in an Excel sheet, every single cost related, engineering costs, material maintenance costs, energy losses, all of these should be thrown into an Excel sheet with real values, of course, no funny numbers. And then based upon it, you calculate and find the net positive value. If you're getting a payback typically of 6 years and less, all plant management will usually support you. If it becomes more than 6 years, that's when you start getting people saying, no, we don't have the money sometimes, things like that. But if you can calculate and show 6 years or less payback, you'll have a strong case. The other issue is that people forget something, and I know too many people, they retrofit, and then let's say the initial cost of the machine originally was worth $3 million, and then they're going to retrofit, and they end up with retrofitting, the costs jump up to $2 million. Many times it was the wrong decision to go for adding 65% costs to an old machine, which is 30 or 40 years old. Would it be much better to remove that machine completely, buy a new one, and put it in its place? And I don't mean the whole skid completely, but if it's a gas compressor, think of going out for bids and just buying a complete gas compressor at $3 million. It's a lot better than spending a long time and large possibility of errors along the way and retrofitting and ending up with $2 million costs. A lot of times it's better to put a brand new machine just as a retrofit replacement. Think about that. Thank you.
Okay, we have one last question from.
I have no problem. By the way, I spoke with Hassan Saloom, and I told him we can go half an hour longer. It says we started late anyway, so we have another 30 minutes. I'm fine to work with, by the way.
All right. Okay. Yeah. The question is, can you comment on the reliability of VSD drives? I'm assuming it's variable speed drives.
Yeah. If he means, I wish he would clarify. Does he mean variable frequency drives, or is he talking about variable speed gearboxes? Which one? Because variable speed gearboxes would be like the ones with brake linings, or the ones with hydraulic, like planetary gearboxes, Voith, or is he speaking variable speed drive like VFD, variable frequency motors? If he could retype his question, it'd be better. We'll go back to his question if we can take the next one.
All right. Okay. Let's just see which one we haven't covered yet. We have a student who is asking, where would you recommend or suggest a mechanical engineer do his co-op training? That's a bit very broad.
Yeah, co-op definitely. I would hope that the college engineer, when he was in college, developed certain interests along the way in his college. If he liked energy, then he should try to get a co-op in energy company. If he liked machinery, he should get a co-op where people are operating a lot of machinery, or at least repairing them. If he has liked plant management, things like this, then he should go to a plant where he can maybe have an assistant to the plant manager. That would be an interesting job, because the plant managers don't have an official assistant job, by the way. However, because they might be the one, that's it. There's only one plant manager, and they don't have the salary code to open it. But if you come in as a co-op, the cost is nothing to them. You say, I'd like to work as a plant manager assistant, and I'm not the decision maker, you are, but I want to be the assistant so I can learn as much as possible. So everything depends on what your skills are, and find the companies that can give you something that interests you in that. And by the way, most companies, they're happy to work with co-op students. They're not, as a co-op, it's considered, he's not a permanent employee, so they don't lose money on you. There's not much lost. They don't feel you affect anybody there at work. They're happy to share their knowledge with co-op students. Okay.
For the clarification, it's variable frequency drives.
Okay. Our experience is, variable frequency drives are great up to maybe 2 megawatt. They're very reliable, excellent. So definitely up to 2 megawatt, they're great. You could use other variable speed devices, but their reliability is good. Once you exceed 2 megawatt, the reliability drops, especially going to 5 and 10 and 15. So as per our experience, obviously you speak to the VFD manufacturers, they'll say no. But from our experience is that they're really good in the smaller scale. If you go to the larger scale, the problem is the components, which are the thyristors and other diodes, which are responsible for changing the AC to the DC signal, then DC back to AC, and giving you a final change in frequency, 10 hertz, 20, 30, 40, 50, 60, they end up having their own electrical failures, these component failures. And it becomes a headache to start to find out, okay, where the failure come from. They also have cooling water systems and cooling air systems, where if you're working with 2 megawatts and below, they're air cooled. So you don't need any liquid cooling, which was much less complicated and more reliable from that aspect. Of course, the VH variable frequency drives we're talking about have to be placed in an air-conditioned enclosures or in the air-conditioned substation with nice, clean, filtered air. That's well known, and it's critical to know that. You don't want to be having an old plant where you don't have a large enough air-conditioned space, like in a substation or other, that doesn't have there's no room available for these VFD units. If you do that, you can't put them outside. You're going to kill them. The moisture will kill them, dust will kill them, and they definitely have to be indoors in an air-conditioned location. But even then, even when they're indoors in an air-conditioned location, as their size gets larger, their reliability drops. So if they were the only choice we had, we'd say, okay, fine, maybe we don't have any other choices. But above 2 megawatt, definitely you can still go for variable speed gearboxes. They're efficient. Nowadays, you have modern, very high efficiency gearboxes from Hitachi, from Voith. Hitachi has some new modern high efficiency planetary gearboxes. Voith has been doing it for 30 years almost now, 28 years maybe, 28 years. There's a few others in the market now, some new ones also. If you want 100 horsepower, 500 horsepower, 1000, at that point you can also use variable speed magnetic couplings. And they also, some are fixed adjustable speed, and others are fully variable speed. So these are called magnetic couplings. And actually, it's funny that you brought us this subject. We have a magnetic coupling here. I don't know if it can be seen. Is it clear here what's in front of the camera?
If you could just lift it a little bit.
Okay. I don't think it's connected to wire. Just a second. Let me see if it's connected. No. You connect electricity. Okay. Now we're on to variable speed, gentlemen. Let's see if we can get it off. Is it clear now?
Yes.
Okay. Here we have a magnetic coupling. I'll reduce the speed by moving the magnetic coupling from the motor side away from the driven side. As you can hear from the noise, the driven fan on the left, which has magnets on the hub and side, also magnets or a copper winding on the motor driven hub, is now running slowly because there's hardly enough magnetic force transferring power from the motor to the driven machine. Now, as I bring them closer, listen to how the sound changes. You see, the RPM has increased. Okay, so this is a magnetic coupling. Now we'll go full speed. And we have full power and full speed, and you're transferring now almost the same speed on the left-hand driven machine. Okay, let's put this off to the side. Okay, looks like today's show and tell.
All right,
Okay.
we have another question that says, what information can be gained from a failed or fractured component, such as a wire rope or something similar?
Oh, okay. Yes, good. It depends on what lab skills that you have. For example, in large corporations, sometimes they have their own lab, failure analysis lab, metallurgical lab. In that case, you can send it to them and they can give you information on the quality of the metallurgy, why it failed, was it fatigue failure? Because if it's a wire rope, you really can't see the individual wires very well to see how they failed. So really would need more likely a specialist lab. However, if it's a lifting rope or other critical wire rope, it's very important to find out why it failed, and a metallurgical lab is very important. So you can always go to a third-party lab, and their costs are not high, and send them the parts and say, look, we need analysis, but please notice one thing: never clean them. Whatever the as found condition, keep it as it is, and send it to the lab. Wrap it in the fracture surfaces, wrap them in a rag, a clean white cotton rag, and then tape over that rag completely. So the fractures, then put it in a box which is protected, strong box, and send it for lab analysis. Now, I wouldn't learn much from the wire as it is broken in front of me, because number one is, it could be things that we cannot judge in front of our eyes. The metallurgy might be cheap quality. You never know, now, especially nowadays. Too many low quality wires and bolts and nuts and everything metallurgic made. Could be it's a cheated, fake origin cable, sold as a normal expensive cable, but it's actually cheap, very cheap metallurgy. Number one, that could be the failure mode. Number two, it might be corrosion if there was in a corrosive environment where water and salt, whatever, have been hitting this wire. Because he said it's a wire rope, for example. It could be fatigue failure, because the wire ropes, they have a certain angle that you're not allowed to exceed. As they go over for example, sheath. Okay, based upon the diameter of the wire rope, it should not be bent to a certain extreme angle. Otherwise, you're causing fatigue failure every time it moves. Just like you can break a paper clip in your own hands by exceeding its ductility limit. And the same thing with the wire ropes. So sometimes it's a design failure, that the wire ropes were installed in a machine or in mining or others, that the angle is too large, and then the wire, as it's going back and forth over it, it's fatiguing. It's not only being in a nice ductile bending. No, it's actually getting a point where it's gradually deforming and then failing. So, and then again, there's also something in the old days, wire rope specialists, and they would know more also. I'm not a wire rope specialist, but we know metallurgical failures.
All right. We have another question saying that there's a gray area between the specialties of CBM, rotating engineer, and vibration engineer, and sometime reliability. What's your opinion on that?
Okay, there's a gray area between CBM, condition-based monitoring engineer, and the rotating engineer and vibration, and then sometimes vibration. It's true. Yes, he's right. There is. Nowadays, you have people who are CBM engineer, others who are rotating equipment engineer. The other is a vibration engineer. It's true. We have this even in our company, by the way. I believe it's because some people are only able to achieve specialization and not able to achieve multiple skills, like both a rotating equipment plus a CBM plus reliability engineer. It's multiple skills here, and some are not able to achieve all three, or they didn't get the experience, the opportunity to learn all three. So they decided, okay, I will become good in one. So fine, it depends on the company. If some companies want just a CBM engineer, then you're valuable. Other times, no, they want a guy who's an engineer, or girl or guy, who is a vibration engineer and rotating equipment together, both at the same time, or CBM and rotating, or reliability who also does rotating equipment. Like this. I personally like to do all of them: CBM, rotating, vibration, and reliability. I believe that, of course, you become better when you have all the skills together.
Excellent. We have another question that's asking about the magnetic coupling. I think they were interested with your little live demo.
Well, they brought in, the questions today. By luck, everything I have on my table.
So the question goes, is there any possibility to use magnetic couplings with fin-fan belt drive applications? Can we use temperature as an input to control the speed?
Oh, I see. So they want to use he means the process temperature in the fans that they require. So they want to vary the speed using the this. Actually, yes, I didn't think of this specific one. You'd have to modify it. What happens is he's talking about a normal fin fan, which is a, let's see if I can pull it out. I don't know if I can pull out a fin fan here. It might take time, but we have a motor on one side with a belt Then the belt drive is a low-speed pulley, might be 220 RPM, and that pulley has a shaft, low-speed shaft going upward vertically, and it turns a large propeller fan, which is, who knows, 15 feet, 20 feet diameter, 25 feet diameter. So he's saying, can we use a magnetic coupling here? Actually, we never thought of it before because we were already coming to another technology, which is direct drive fans. Here we have, instead of the pulley and the belts and the motor, the normal motor at 1800 RPM motor, driving a pulley which is running with V-belts running at 250 or 200 RPM, then driving that upper fan shaft, just driving the fan. We eliminate all this. You eliminate the small motor, you eliminate the belt, you eliminate the pulleys, you eliminate the big, long, low-speed shaft, put a single motor, which is a constant speed fan, okay? And I guess I can pull it out if you just give me 1 second here. I can pull out a drawing or a picture of it is better, so we can just show it here. Desktop fans, low speed fans, low speed direct drive. Okay, here we go. So we have low speed direct drive fans. I will share this with our screen if I can find the share. Okay, there's a sharing and screen share. Okay, share your screen. Yes. Should I like share? I don't know. Is it working? I don't think it's not sharing yet.
Once you click share, you're supposed to click desktop or window.
Okay, here we go. Finally. Okay, so I'm seeing you. Okay.
All right, there we go.
There we go. Okay, so let me pull it out full. Is it clear now?
Yes.
Okay. So I don't know if I can move this down. There. So this is the typical technology of, at least this is a motor-driven fan on the left-hand side, motor with a long drive shaft, but you don't see the motor here. Then you have a gearbox, then you have a fan. This is a cooling tower fan. And here's the new technology, which is much better. It's a direct-driven, special-made motor that is made to live inside these water cooling towers. By the way, it's a waterproof almost, designed to live in continuously in this environment. And there's no more shaft now going back to a motor outside. So you eliminated the motor and the drive shaft and the gearbox. And well, you still have a motor, but it's a large, low-speed direct drive motor that drives the hubs directly. Okay, so we eliminated the gearbox and the drive shaft, and the small motor's gone. Now we have a large motor. So this is not exactly what he was discussing. He was discussing more the fin fans. But so this is the one we just talked about just now. This is the old technology, motor outside. Then you have a shaft, lone shaft, and gearbox and fans. And we are going toward, and this is again a situation. The other situation is fin fans. Here's the belted drive. So here's the belted drive. I believe Mr. Feiruz was discussing this. Can we add a magnetic coupling to this drive here? Okay, instead of this technology, which is direct drive, which works also, he wants to use this technology. Sorry, we lost the page there. Yes, it's possible. You'd have to have a you'd put here, it's salt. You'd put here a sheave, but it has to have a third bearing or a second bearing out here to support this sheave, because they're going to be a magnetic sheave with a magnetic pulley on it, and then you would have adjustable speed. Okay, and that would then connect to the same old pulley. So the rest of your infrastructure would stay the same, but this side has to be modified. And it's possible you could probably use, again, you can probably use the same motors, but you have to add this special sheave with a special bearing support for it somehow. That has to be added over here. So is it possible? Yes, you could. The other thing that people do is in this old installation is they just put a VFD motor. Okay, the only problem is, okay, if you put a VFD motor here instead of the old variable frequency drive, that will do the job fine. The only problem is that the VFD, you cannot use an external cooled, a normal one in ambient temperatures. You have to take that VFD and put it in some cooled building a certain distance away, and that is going to be a large infrastructure and cost and everything. And that's most of the costs. It's not so much the VFD motor, but the whole connection and the expense of that becomes too expensive. So definitely a magnetic coupling here could work. Yes, it's possible. Or if possible, go straight to a direct drive motor, but this is in a cooling tower application. If you're going to put a direct drive motor in an induced draft or forced draft, I would say not induced, but in forced draft, it's also possible. This is a forced draft fan. So you eliminate the previous connections here, all of these, the low speed shaft and this pulleys and everything, and you jump straight and put in this low speed motor up here, directly driving the fan, but only in forced draft application, not in induced draft. We cannot do it with a low speed shaft induced draft because you cannot put a low speed bearing motor here, then you have a long shaft on top. It doesn't work really properly well. You still end up having a bearing up there. I guess you could, but it's not really recommended. This is the more easier recommended. Okay. Good.
All right.
Let me just stop sharing this. I'll just stop sharing that. I hope we can switch back to normal this way. Escape. And okay, so can you bring me back up on the screen? Let's see, turn camera on. Okay, I need to stop sharing.
All right, you're back.
Yeah, I'm not back? Okay.
All right.
Okay.
I think we are at the end of our session. On behalf of ASME ESAS, I'd like to thank you once again for joining us in this. You've been tremendously, this was a very tremendous experience. I'm sure everyone gained a lot from this, and you've answered a lot of questions. We hope to see you again in one of our other sessions, hopefully. And if anyone has any questions, I'm sure they can reach out to you. You're available on LinkedIn, I think, correct? Or
that's correct, yes. Yes.
Yes, or you could just contact him directly. Or if you type any of your questions, I'm sure Abdulrahman will try to get to him if possible.
Thank you, gentlemen. Appreciate it, and maybe we'll have another session sometime in the future.
Inshallah. All right. Thank you.
Thank you.
All right.
Thank you, Abdulrahman, and special thanks to Muhammad as well.
Thank you.